So now we have a student is riding a bicycle with a total mass m with the speed of v. It has to go up a circular hill with the radius r. Assume that the wheels have a negligible mass and there's no kinetic friction, and the student is not pedaling. Okay. What is the minimum speed needed for the bicycle to make it over the hill? Well, to make it over the hill, so we're going to start down here. So there's no friction and we're not pedaling. That means there's no outside work on the system, so the energy is not changing in the system. Assuming the system is the student plus Earth plus bicycle. Okay, so that's our system. So all we need to do is really just need to talk about what would it take for him to go up here, right? So we start down here, and we have some kinetic energy, right? We have no potential. So the kinetic energy is 1/2 mv squared. The potential energy, because we're including the Earth in the system, is 0. Now, why do we include the Earth? When you're going up something or you're changing heights, it's natural to include the Earth so you can use conservation of energy. I think it's easier to do that than to think of excluding the Earth and trying to do the work done by gravity, right? Because if you exclude the Earth, then gravity is an external force, and then you have to calculate the work done by that to cause the change in energy. So it's better to include the Earth in these kinds of situations so that you can just set the energies equal to each other. Okay, here, if you want to just make it over the hill, you want the velocity to be 0 over here, because you want to make it just to the top and then come to a stop. That's how you just made it over the hill. Okay, so that means the kinetic energy here is 0, and the potential energy is equal to mgh. Well, so what's the height? So what is the mgh? It's mg times r, technically, because r is the height above the ground. So here we're going to say the two energies are equal to each other. The total energy here equals the total energy here because there's no work, right? So we're going to say 1/2 mv squared is equal to mgr. M's cancel. And you want to solve for v. So that means v squared, multiply both sides by 2. 2gr. V equals root 2gr. Okay. B, what is the maximum speed v the bicycle can have so that it still remains in contact with the ground? So now we're talking about, okay, now I go faster than the minimum, so I'm going fast. So what happens is, if you go down here, you're going to go faster and you're going to have some kinetic energy. So the change is we're going to have some kinetic energy here. We're going to have only kinetic energy here, and at the top we're going to have kinetic energy and gravitational potential energy. Now, why is there a maximum? What happens if I go too fast is you lose contact. You'll just launch. It'll be like a ramp. You'll just launch off, right? So how do we handle it so we remain in contact with the ground? Well, if you want to just barely maintain contact, that means the normal force is about 0. You want to know when the normal force is when you're barely touching the ground, that means the ground can't push on you, and so that normal force is to be 0. So we look at a free body diagram of the guy up here and we say, okay, well, I have gravity going down and I have a normal force going up, but the normal force is 0, so there is no normal force. There's no friction and nothing else is touching the bicycle and the student, so the only force is mg. Now, what happens after you draw the free body diagram? So the net force is equal to mg, and that's equal to ma. Okay? Now, we need it to what kind of acceleration? Well, it's a circular ramp. So as we travel around this path, we're going in a circle. That acceleration is centripetal acceleration. Okay. So that what I need here is I need the v at the top. So this v is at the top of the hill. I need the v at the top of the hill to so I have, let's just prove it out. Mg equals mv squared over r. The m's cancel if I divide by both sides. That means v squared is equal to gr. That means I need the v at the top of the hill to be the square root of gr. Now that's at the top of the hill. I need to know what the speed is at the bottom of the hill, though. All right. So here's where we're going to do conservation of energy. we're going to say 1/2 m, I'm going to call it v bottom, has to equal mgr, the gravitational potential energy, plus 1/2 m v top squared. All right, and I want to know the velocity at the bottom. So this is 1/2 m v bottom squared is equal to mgr. And all I'm going to do is plug in v top squared is just gr plus 1/2 mgr. Okay, I have 1 mgr and a half of mgr. That's 1.5 or 3/2 mgr. Okay, the m's on both sides will cancel. Multiply by 2 both sides, that cancels with that. And so that the v at the bottom has to equal square root of 3gr. Okay, so that's the maximum speed. So the minimum speed to get over the hill is square root of 2gr, and the maximum is, before I start launching or hopping off the hill or losing contact with the ground, is square root of 3gr.